All right, let's do this. Today, we're going to take a journey deep inside the atom. We're going to explore one of the biggest, most mind-bending shifts in all of science. The story of how our picture of the atom went from a tiny little solar system to a fuzzy, bizarre, probabilistic cloud. Okay, let's dive right in. So, let me just ask you, what does an atom really look like? I mean, if you close your eyes and picture one right now, I bet you're seeing a little nucleus in the center with electrons just zipping around it in perfect circles, kind of like tiny little planets, right? It's a powerful image for sure, but it's not the whole story. It's not even close, actually. You see, that simple little solar system model? It had a huge, and I mean a fatal flaw. According to all the rules of physics at the time, an electron whipping around like that should be constantly giving off energy. And if it's losing energy, it should spiral right down into the nucleus in like a split second. If that were true, well, nothing could exist. Not you, not me, not anything. Atoms, by all rights, should have been completely unstable. And then, this guy, Niels Bohr, comes along with a pretty radical solution. His model was this incredible stepping stone. I mean, on the one hand, it was a massive success. It perfectly explained why hydrogen atoms give off very specific colors of light, and it gave us the idea of energy levels. But it couldn't explain why atoms were stable in the first place, and it basically fell apart for any atom bigger than hydrogen. So what was Bohr's big idea? It all boiled down to this one concept: quantization. He basically just declared, against everything people thought they knew, that electrons weren't allowed to orbit just anywhere they wanted. No, they were restricted, forced to exist only in these specific, fixed, circular paths, each with its own precise energy level. It was a brilliant rule, but that's all it was, a rule without a reason. And he backed it up with this incredibly elegant formula. This little equation right here was huge. It let him perfectly predict the energy for every single allowed orbit in a hydrogen atom. You just plug in the orbit number, n equals 1, 2, 3, and boom, you get the right answer. The math just worked. It was amazing. But it left this one giant nagging question just hanging in the air. Exactly. Why? What was so special about these particular orbits? Why this weird restriction? Bohr's model was like a brilliant cheat sheet. It gave all the right answers for hydrogen, but nobody could figure out the deeper reason why it worked. Science needed a reason, not just a rule. And the answer? Well, it came from a place no one expected. And this is where the story gets really good. A young physicist, Louis de Broglie, steps onto the scene and asks a question that must have sounded absolutely crazy at the time. He said, what if particles, like our little electron, what if they also behave like waves? It sounds impossible, right? How can a tiny solid dot also be a spread-out wave? But that one question was the key that unlocked the whole mystery. So how does this wave idea fix everything? It all comes down to something called a standing wave. Think about a guitar string. When you pluck it, it doesn't just flop around randomly. It vibrates in these nice, stable patterns. For an electron's wave to be stable as it goes around the nucleus, it has to fit perfectly into the circumference of its orbit. It has to meet up with itself smoothly. If it doesn't fit, if the circumference isn't a whole number of its wavelength, the wave interferes with itself and just cancels out. Poof, it's gone. And just like that, you have a physical reason for Bohr's rules. Only certain orbits are allowed because they're the only ones where the electron's wave can actually exist. De Broglie's crazy idea wasn't just a patch for the old model. Oh no, it was the spark that ignited an entirely new kind of physics. It was the conceptual breakthrough, and scientists like Schrödinger realized they needed a whole new mathematical framework to describe how these matter waves work. And that new framework? That's quantum mechanics. This new physics, it just throws the whole idea of a neat little orbit right out the window. Gone. Instead, an electron is described by something called a wave function, which we write with the Greek letter psi. Now, this isn't a physical wave in the ocean. It's a pure mathematical description, but it contains everything there is to possibly know about the electron: its energy, its momentum, the whole shebang. And here's the quantum leap, the part that gets really weird and cool. If you take that wave function and you do a little math, you square its magnitude, you don't get the electron's exact location. You can't. Instead, what you get is the probability of finding the electron at any particular spot in space. We have to trade the certainty of a fixed path for a map of likelihood. And this idea brings us to our modern picture of the atom. We don't talk about orbits anymore. We talk about orbitals. And these orbitals aren't paths. They are three-dimensional regions of probability. It's a total shift in how we see the universe, from a predictable clockwork machine to one that's fundamentally based on chance. So, welcome to the electron cloud. So let's look at the simplest one, the s orbital. It's a sphere, a cloud of probability. It is not a solid shell. It's not a path. Where the cloud looks denser, that just means there's a higher probability of finding the electron there at any given moment. This cloud is the real picture of an electron in its lowest energy state. And honestly, understanding these shapes is the foundation of all modern chemistry.
So let's just recap this incredible story. First, you have Bohr. He gives us the groundbreaking idea of quantized energy levels, a brilliant rule that worked but didn't have a reason. Then de Broglie comes in and gives us that beautiful physical reason. The electron is a standing wave. And finally, Schrödinger builds the complete mathematical picture with the wave function, giving us these strange, wonderful clouds of probability we use today. What a journey.
And that leaves us with one final, kind of mind-bending thought to chew on. Everything around you that you think of as solid, the chair you're in, the device you're watching this on, it's all made of these atoms. And these atoms are mostly empty space, defined by these fuzzy, ghostly clouds of probability. So, if that's the fundamental reality of matter, what does it even mean for something to be solid? Pretty wild, huh? Thanks for joining me.